Good day. So for this topic, I will discuss to you guys about virtual memory. Virtual memory is a technique that allows the execution of processes that are not completely in memory. One major advantage of this scheme is that programs can be larger than physical memory. Virtual memory also allows processes to share files easily and to implement shared memory. In addition, it provides an efficient mechanism for process creation. Virtual memory is not easy to implement. However, it may decrease performance if it used carelessly. So, in this chapter, we discuss virtual memory in the form of demand paging and examine its complexity and cost. So, for our objectives, to describe the benefits of virtual memory system, to explain the concept of virtual memory, and to explain the concepts of demand paging and page replacement. The background of virtual memory. The instructions being executed must be in physical memory. The first approach to meeting this requirement is to place the entire logical address space in physical memory. Dynamic loading can help to ease this restriction, but it generally requires special precautions and extra work by the programmer. The requirement that instructions must be in physical memory to be executed seems both necessary and reasonable, but it is also unfortunate since it limits the size of the program to the size of physical memory. In fact, examination of real programs shows us that in many cases the entire program is not needed. For instance, consider the following. First is, programs often have code to handle unusual error conditions. Since these errors seldom if ever occur in practice, this code is almost never executed. Second, arrays, lists, and tables are often allocated more memory than they actually need. An array may be declared 100 by 100 elements, even though it is seldom larger than 10 by 10 elements. An assembler symbol table may have room for 3,000 symbols, although the average program has less than 200 symbols. Next consideration is, certain options and features of the program may be used rarely. For instance, the routines of US government computers that balance the budget are only rarely used. Next is, a program would no longer be constrained by the amount of physical memory that is available. And because each user program could take less physical memory, ignore programs could be run at the same time with a corresponding increase in CPU utilization and throughout, but no increase in response time or turnaround time. Last is, less input-output would be needed to load or swap each user program into memory, so each user program would run faster. As you can see in the picture, this is figure 9.1, the diagram showing virtual memory that is larger than physical memory. Running a program that is not entirely in memory would benefit both the system and the user. Virtual memory involves the separation of logical memory as perceived by users from physical memory. This separation allows an extremely large virtual memory to be provided for programmers when only a smaller physical memory is available. Virtual memory makes the task of programming much easier because the programmer no longer needs to worry about the amount of physical memory address space of a process refers to the logical view of how process is stored in memory. So, in fact, physical memory may be organized in page frames and that the physical page frames assigned to a process may not be continuous. It is up to the memory management unit to map logical pages to physical page frames in memory. The next figure is all about virtual address space, that we allow for the heap to grow upward in memory as it used for dynamic memory allocation. Similarly, we allow for the stack to grow downward in memory through successive function calls. The large blank space, or the hole, between the heap and the stack is the part of the virtual address space but will require actual physical pages only if the heap or stack grows. Virtual address spaces that include holes are known as space address spaces. Using a space address space is beneficial because the holes can be filled as the stack of heap segments, or we wish to dynamically link libraries or possibly other shared object during execution. So in addition to separating logical memory from physical memory, virtual memory also allows files and memory to be shared by two or more processes. This leads to the following benefits. First, system libraries can be shared by several processes through mapping of the shared object into a virtual address space. Although each process considered the shared libraries to be part of its virtual address space, the actual pages where the libraries reside in physical memory are shared by all the process. So next is, similarly, virtual memory enables processes to share memory. The last benefit is virtual memory can allow pages to be shared during the process creation with the fork system call, thus speeding up process creation. So that's it. The next picture, as you can see, is shared library using virtual memory. Processes sharing this region considered it part of their virtual address space, yet the actual physical pages of memories are shared. Let's now proceed to demand paging. Consider how an executable program might be loaded from disk into memory. One option is to load the entire program in physical memory at program execution time. However, a problem with this approach is that we may initially need the entire program in memory. Consider a program that starts with a list of available options from which the user is to select. Loading the entire program into memory results in loading the executable code for all options, regardless of whether an option is ultimately selected by the user or not. An alternative strategy is to initially load pages only as they needed. This technique is known as demand paging and is commonly used in the virtual memory system. With demand page, virtual memory pages are only loaded when they are demanded during program execution. Pages that are never accessed are thus never loaded into physical memory. This next picture shows us a transfer of a page memory to contiguous disk space. A demand paging system is similar to a paging system with swapping, where processes reside in secondary memory, usually a disk. When we want to execute a process, we swap it into memory. Rather than swapping the entire process into memory, however, we use a lazy swapper. So, a lazy swapper never swaps a page into memory unless that page will be needed. Since we are now viewing a process as a sequence of pages rather than as one large continuous address space, use of the term swapper is technically incorrect. A swapper manipulates the entire processes, whereas a pager is concerned with the individual pages of a process. We thus use pager rather than swapper in connection with demand paging. When a process is to be swapped in, the pager guesses which pages will be used before the process is swapped out again. Instead of swapping in a whole process, the pager brings only those necessary pages into memory. Thus, it avoids reading into memory pages that will not be used anyway, decreasing the swap time and the amount of physical memory needed. The basic concepts. When a process is to be swapped in, the pager guesses which pages will be used before the process is swapped out again. Instead of swapping in a whole process, the pager brings only those necessary pages into memory. Thus, it avoids reading into memory pages that will not be used anyway, decreasing the swap time and the amount of physical memory needed. As you can see in this picture, this is figure 9.5, the table when some pages are not in main memory. So notice that the marking of a page invalid will have no effect if the process never attempts to access that page. Hence, if we guess right at the page in all those pages that are actually needed, the process will run exactly as though we had brought in all pages, while the process executes and accesses pages that our memory resident execution proceeds normally. As you can see in this picture, it shows the steps in handling a page fault. The procedure for handling this page fault is straightforward. So for the next slide, I will explain to you each steps for this. But what happens if the process tries to access a page that was not brought into memory? Access to a page marked invalid causes a page fault trap. The paging hardware, in translating the address through the page table, will notice that the invalid bit is set, causing a trap to the operating system. So this trap is the result of the operating system's failure to bring the desired page into memory. So this is the 6 steps in handling page fault. First, we check an internal table usually kept with the process control block for this process to determine whether the reference was a valid or an invalid memory access. Second, if the reference was invalid, we terminate the process. If it was valid, but we have not yet brought in that page, we now page it in. Third, we find the free frame by taking one from the free frame list. Fourth, we schedule a disk operation to read the desired page into a newly allocated frame. When the disk read is complete, we modify the internal table kept with process and the page table to indicate the page is now in memory. Sixth, we restart the instruction that was interrupted by the trap. The process can now access the page as though it had always been in memory. The hardware to support demand paging is the same as the hardware for paging and swapping. So page table, this table has the ability to mark an entry invalid through a valid invalid bit or special value of protection. While secondary memory, this is memory holds those pages that are not present in main memory. The second memory is usually a high-speed disk. It is known as the swap device, and the section of disk used for this purpose is known as the swap space. A crucial requirement for a demand paging is the need to be able to restart any instruction after a page fault, because we save the state registers conditions code instruction counter of the interrupted process when the page fault occurs. We must be able to restart the process in exactly the same place and the state, except that the desired page is now in memory and is accessible. In most cases, this requirement is easy to meet. A page fault may occur at any memory reference. If the page fault occurs on the instruction fetch, we can restart by fetching the instruction again. If a page fault occurs while we're fetching an operand, we must fetch and decode the instruction again and then fetch the operand. As worst case example, consider a 3-address instruction such as ADD, the content of A to B, placing the result in C. These are the steps to execute this instruction. First, fetch and decode the instruction ADD. Fetch A. Third, fetch B. Add AB, and lastly, store the sum in C. If we fault when we try to store in C because C is in a page not currently in memory, we will have to get desired page, bring it in, correct the page table, and restart the instruction. The restart will require fetching the instruction again, decoding it again, fetching the 2 operands again, and then adding again. However, there is not much repeated work, less than 1 complete instruction, and the repetition is necessary only when a page fault occurs. Next is performance of demand paging. Demand paging can significantly affect the performance of a computer system. To see why, let's compute the effective access time for a demand page memory. For most computer systems, the memory access time denoted MA ranges from 10 to 200 nanoseconds as long as we have no page faults. The effective access time is equal to the memory access time. However, a page fault occurs, we must first read the relevant page from disk and then access the desired word. Let P be the probability of page fault 0SP51. We would expect P to be close to 0, that is, we would expect to have only a few page faults. The effective access time is then effective access time is equal to 1 minus P times MA plus P times page fault time. To compute the effective access time, we must know how much time is needed to service a page fault. A page fault causes the following sequence to occur. First, trap to the operating system, save the user registers and process state, determine that the interrupt was a page fault, and check the page reference was legal and determine the location of the page on the disk. Fifth step, issue a read from the disk to a free frame. Wait in a queue for this device until the read request is serviced. Wait for the device seek and/or latency time. Begin the transfer of the page to free frame. 6. While waiting, allocate the CPU to some other user. CPU scheduling is optional. 7. Receive an interrupt from the disk input-output subsystem and input-output completed. 8th step is save the registers and process state for the other user if step 6 is executed. 9th, determine that the interrupt was from the disk. 10th, correct the page table and other tables to show that the desired page is now in memory. 11, wait for the CPU to be allocated to this process again. And lastly, restore the user register's process state and new page table and then resume the interrupted instruction. Not all these steps are necessary in every case. For example, we are assuming that in step 6, the CPU is allocated to another process while the input-output occurs. This arrangement allows multi-programming to maintain CPU utilization but requires additional time to resume the page fault service routine when the input-output transfer is complete. In any case, we are faced with three major components of the page fault service time. First, service the page fault interrupt, read in the page, and restart the process. That is the three major components of the page fault service time. Next is copy on write. A process can start quickly by merely demand paging in the page containing the first instruction. However, process creation using the fork system call may initially bypass the need for demand paging by using a technique similar to page sharing. This technique provides for rapid process creation and minimizes the number of new pages that must be allocated to the newly created process. So recall the fork system. Call creates a child process as a duplicate of its parent. Traditionally, fork worked by creating a copy of the parent's address space for the child, duplicating the pages belonging to the parent. However, considering that many child processes invoke the exec system call immediately after creation, the copying of the parent's address space may be unnecessary. As you can see in this picture, this is figure 9.7 and figure 9.8. This is the before process of 1 modifies page C and after process of 1 modifies page C. It shows that the contents of physical memory before and after process 1 modifies page C. For example, assume that the child process attempts to modify a page containing portions of the stock with the pages set to be copy on write. The operating system will then create a copy of this page, mapping it to the address space of the child process. The child process will then modify its copied page and not the page belonging to the parent process. Obviously, when the copy on write technique is used, only the pages that are modified by either process are copied. All unmodified pages can be shared by the parent and child processes. Next topic is the replacement. If a process of 10 pages actually uses only half of them, then demand paging saves the input-output necessary to load the 5 pages that are never used. We could also increase our degree of multi-programming by running twice as many processes. Thus, if we had 40 frames, we could run 8 processes rather than the 4 that could run if each required 10 frames, 5 of which were never used. If we increase our degree of multi-programming, we are over-allocating memory. If we run 6 processes, each of which is 10 pages in size but actually uses only 5 pages, we have higher CPU utilization and throughput. With 10 frames to spare, it is possible, however, that each of these processes for a particular dataset may suddenly try to use all 10 of its pages, resulting in a need for 60 frames when only 40 are available. Figure 9.9 shows the need for page replacement. The operating system determines where the desired page is residing on the disk, but then finds that there are no free frames on the free frame list. All memory is in use. The operating system has several options at this point. It could terminate the user process. However, demand paging is the operating system attempt to improve the computer system's utilizations and throughput. Users should not be aware that their processes are running on a page system. Paging should be logically transparent to the users. The basic page replacement. Page replacement takes the following approach. If no frame is free, we find one that is not currently being used and free it. We can free a frame by writing its content to swap space and changing the page table to indicate that the page is no longer in memory. So, basic page replacement, we can now use freed frame to hold the page for which the process faulted. We modify the page fault service routine to include page replacement. First is find the location of the desired page on the disk. Find a free frame. If there's a free frame, use it. If there's no free frame, use a page replacement algorithm to select a victim frame. Select or write the victim frame to the disk and change the page and frame tables accordingly. Third is read the desired page into newly freed frame. And last, restart the user process. Notice that if no frames are free, 2 pages transfer, 1 out and 1 in, are required. This situation effectively doubles the page fault service time and increases the effective access time accordingly. We can reduce this overhead by using a modified bit or dirty bit. When this scheme is used, each page or frame has a modified bit associated with it in the hardware. So figure 9.10 is a page replacement. Page replacement is basic to demand paging. It completes the separation between logical memory and the physical memory. With this mechanism, an enormous virtual memory can be provided for programmers on a smaller physical memory. With no demand paging, user addresses are mapped into physical addresses. So the two sets of addresses can be different. All the pages of process still must be in physical memory. However, with demand paging, the size of the logical address space is no longer constrained by a physical memory. If we have a user process of 20 pages, we can execute it 10 frames simply by using demand paging and using a replacement algorithm to find a free frame whenever necessary. We must solve two major problems to implement demand paging. We must develop a frame allocation algorithm and a page replacement algorithm. If we have multiple processes in memory, we must decide how many frames to allocate to each process. Further, when page replacement is required, we must select the frames that are to be replaced. Designing appropriate algorithms to solve these problems is an important task because this input-output is so expensive. Even slight improvements in demand paging methods yield large gains in system performance. The string of memory references is called a reference string. We can generate reference strings artificially by using a random number generator, or we can trace a given system and record the address of each memory reference. The latter choice produces a large number of data on the order of 1 million addresses per second. So, to reduce the number of datas, we use two facts. First, for a given page size, and the page size is generally fixed by the hardware system, we need to consider only the page number rather than the entire address. Second, if we have a reference to a page P, then any immediate following reference to page P will never cause a page fault. For example, if we trace a particular process, we might record the following address sequence. These are the sequence as you can see on the monitor on the screen. And at 100 bytes per page, this sequence is reduced to the following reference string. The next page replacement is FIFO page replacement, the first in, first out. The simplest page replacement algorithm is a first in, first out or FIFO algorithm. A FIFO replacement algorithm associates with each page the time when that page was brought into memory. When a page must be replaced, the oldest page is chosen. Notice that it is not strictly necessary to record the time when a page is brought in. We can create a FIFO queue to hold all pages in memory. We replace the page at the head of the queue. When a page is brought into memory, we insert it all the tail of the queue. For example, the reference string or 3 frames are initially empty. So, as you can see in figure 9.12, the FIFO page replacement algorithm, the first 3 references, 7, 0, and 1, cause page fault and are brought into these empty frames. The next reference replaces page 7 because the page 7 was brought in first. Since 0 is the next reference and 0 is already in memory, we have no fault for this reference. The first reference to 3 results in replacement of page 0 since it is now first in line. Because of this replacement, the next reference to 0 will fault. Page 1 is then replaced by page 0. This process continues as shown in this figure. Every time a fault occurs, we show which pages are in our 3 frames. There are 15 faults together. The FIFO page replacement algorithm is easy to understand and program. However, its performance is not always good. On the hand, the page replace may be an initialization module that was used a long time ago and is no longer needed. On the other hand, it could contain a heavily used variable that was initialized early and is constant is used. The next replacement is optimal page replacement. An optimal page replacement algorithm has the lowest page fault rate of all algorithms and will never suffer from belay this anomaly. Such as algorithm that exists and has been called OPT or MIK. One result of the discovery of belay this anomaly was the search for an optimal page replacement algorithm. This is use of this page replacement algorithm guarantees the lowest possible fault rate for a fixed number of frames. For example, on our sample reference string, the optimal page replacement algorithm would yield 9 pages fault. The first 3 references cause faults that fill the 3 empty frames. So, the figure 9.14 optimal page replacement algorithm is used mainly for comparison studies. For instance, it may be useful to know that although a new algorithm is not optimal, it is within 12.3% of optimal at worst and within 4.7% on average. So the reference to page 2 replaces page 7 because 7 will not be used until reference 18, whereas page 0 will be used at 5 and page 1 at 14. The reference to page 3 replaces page 1 as page 1 will be the last of the 3 pages in memory to be referenced again with only 9. Let's now proceed to the applications and replacement. Applications accessing data through the operating system virtual memory perform worse than if the operating system provided no buffering at all. A typical example is a database, which provides its own memory management and in input and output buffering. Applications like this understand their memory use and this use better than the SNAT operating system that is implementing algorithms for general purpose use. If the operating system is buffering the input and output and the application is doing as well, then twice the memory is being being used for a set of input and output. Another example, data warehouses frequently perform massive sequential disk reads followed by computations and writes. And that's it. Thank you for listening. It's all about virtual memory. I hope you had an idea everything I discussed on this topic. Once again, I'm Maria Leila Loyola. Thank you for listening.